G'day folks, my name is Michael Beven. I'm the CEO at Pioneer Lithium, exploration geologist and member of the Australian Institute of Geologists as well. During this presentation, I'm going to go over Pioneer's most recent ASX announcement dated the 2nd of April 2025. Significant radiometric anomalies confirm high priority uranium targets at Skull Creek Project, Colorado. Now, the purpose of this video is for me to review the announcement that we've just put out and break down some of the key components for existing shareholders and future shareholders as well, just so some people can get a better understanding, I guess, of some of the geological terms that we use and some of the true meaning or interpreted meaning behind the maps and the diagrams that we've put out. Now, many of you may be familiar with the videos that I've produced previously for a past endeavor, but many of you may not. And so I just wanted to make you aware that, once again, the purpose of these videos and for Pioneer moving forward as well is really going to be to discuss the merits of the project and the technical aspects of the projects, as opposed to focus on the corporate side of PLN. So you can expect me to go through the geology, the results, the interpretation, what that means, what we're planning on doing, etc., etc., and not so much trying to talk about why you should invest in us and so forth. I really want you to be able to make that decision based off the information that you see that we present and then the merits of their projects alone, as opposed to any sort of standard corporate spin that you might hear with your traditional sort of media. So that's really the focus. That's what you can expect. And without harping on any more, let's get cracking. Right, so ASX announcement, 2nd of April 2025, significant radiometric anomalies confirm high priority uranium targets at Skull Creek Project, Colorado. So initial field exploration identifies 4 highly prospective uranium targets: County Line, Blue Mountain, Skyline, and Railroad. Significant radiometric anomalies associated within the uranium prospective Sego Sandstone. So you're going to hear the word or the words Sego Sandstone a lot as we go through this presentation. This is really our target lithology here and the primary host for where we think the uranium is going to be as well. And we've got, I guess, really quite anomalous and radioactive Sego Sandstone at 11 different locations across those 4 different prospect areas. Peak radiometric anomaly recorded at Blue Mountain Prospect, reading at 10,000 counts, or CPS. So CPS stands for counts per second. And the easiest way to explain this, what this really sort of means is if you've ever, we use a spectrometer to measure this. You would also hear them called Geiger counters in other sort of things. Now, a Geiger counter and a spectrometer are actually technically different, but they very much do the same thing. So they're interchangeable when you hear them referred to in many ways. And what this is really reading is there's a detector on the instrument, and how many times that receives a strike from particles from things with radioactive decay is the count. So it's actually measuring how many counts per second, how many times has that been struck by a particle caused by radiation, per second. And you hear it in the movies or you see it in different things when the little handheld radiation detector starts sort of screaming and beeping and going off. Each one of those little ticks that you hear is measuring a count per second. So each strike, you hear that little noise, and obviously it tells you how many counts per second. You don't have to listen to those, but there is that associated with it. So just so you know sort of what a spectrometer is and basically how it works. Favorable lithologies and geological structures identified and mapped. Now, this is actually probably the key and most important aspect of this announcement. It's something that we'll be talking about a fair bit as well. This is the fundamental basics. This is the very foundation that we need in order for an exploration project to be successful or potentially successful. This is probably the most boring part of a lot of announcements, but as a geologist, an exploration geologist, it's actually one of the key things that we're looking for in the very beginning. 16 rock chip samples were collected from across the Sego Sandstone and across the area, and the radiometric anomalies as well. We sent them to ALS for analysis. We're doing a really quite broad range of assays on them as well, so that we can find all the associated pathfinders and try and get an understanding of any potential mineralization early. We'll talk about that a little bit more as we go and the importance of the different elements, but just thought I want to touch on that now. A strategic land position secured immediately adjacent to Homeland Uranium's TSX HLU uranium exploration projects. So you can go ahead and have a look at Homeland Uranium. you'll see that they have their project just adjacent to ours as well. They're actively looking to explore the Sego sandstone as well, and this will just give you an idea of I guess that we're in quite a competitive environment for uranium mineralization. Experienced uranium exploration and geophysical teams engage to rapidly progress the exploration activities and define drill-ready targets. Very true. We have a fantastic team that we've put together to approach these targets, not just here, but Wombat as well. We've got Mark Cousins, who is a very well-renowned exploration geologist on board to help us with this work. Nick Dyrene from Mida Geophysics, another very well-respected geophysicist and great operator, and then myself as well to approach these. In country, we have Big Rock Exploration, who so far have just done a really good job. I've been really happy with the groundwork that they've done, their understanding of the project area, of the mineralization, and what they're really looking at. So it's excellent to have them on board, and the team is coming together really quite well to be able to approach these projects. Now, I'm not going to read out my own comments. I feel like that would be awkward. Most of what I'm trying to say here, I'm going to talk about in this videos anyways. So nice picture here. You can see a nice outcrop of the Sego sandstone. This is sort of what they're looking for and trying to map. So where these areas of Sego sandstone are outcropping, sticking out of the ground, we can measure them. We can see how they occur relative to other rock types that are sticking out of the ground as well. And then we get a good indication as well as, okay, is this layer radioactive? If it is radioactive, then obviously it's because of radioactive minerals within that layer, and that just increases the prospectivity as well. Not every bit of sandstone, of Sego sandstone, is going to be radioactive. So identifying some layers which are and some that aren't is really quite important and probably good news. If everything was just radioactive, then it wouldn't be important or have exploration significance. But when you find that, you know, individual layers are, then that's when you know they can be a host or are a host for uranium mineralization, and the others are just sort of barren. So that's key as well. Knowing where things aren't is as important as knowing where things are. So you can see just an outline of our tenements here that we hold, and you might think we have some long, skinny tenements here, and we do, but that is okay and actually a good thing, because the Sego sandstone runs east to west here, all the way up through our ground. So pretty much the Sego sandstone here is highlighted by our tenement outline. We've got homeland uranium, which hold the ground around us, and then high test here as well. But the shape of our tenements very much matches the shape of the Sego sandstone. So this is just a quick prospect map which shows, I guess, the 4 main areas which we've found the different radiometric anomalies. These purple traces that you can see are going everywhere. This is just the, I guess, the trace of where our geologist Chris from Big Rock Exploration has actually walked. We use 2 methods here to, I guess, detect the anomalies. There's the radio code 102, which is a device which not only tracks your GPS location, things like that, but also gives you a relative measurement of radiation. So it doesn't give you counts per second like a spectrometer will, but what it does is it will just give you, you'll get a reading that will tell you whether or not it is detecting elevated radiation there or not. Once you detect that elevated radiation, you'll then use the spectrometer to then take more accurate measurements of the area. Now, interestingly, when we plot up the radio code relative changes, they actually plot perfectly with the spectrometer as well. So we know that from the work that we've done here over the Sego sandstone, that if we're getting 400 on the radio code, we can directly correlate that on a linear plot to 6,000 counts per measure, just as an example there. So it's actually worked out to be really quite an accurate tool for measuring radioactive anomaly. Not counts per second, but it correlates with counts per second extremely well. Now we'll start off and take a look at the individual prospects. The first one we're going to discuss is County Line here, and this is just a zoom map, I guess, of the County Line prospect area. and the two different targets that we have within that one area. So David and Moffat. Now these maps are good just so you can obviously see where the different counts per second readings are taken from, but what you can really start to infer a lot more from is when you look at the cross sections, which have been based off geological observations by Chris in the field. That starts to tell a lot more, I guess, more of a story and the importance of these actual radiometric anomalies. So like I said before, you have areas of the Seco sandstone which aren't anomalous, but then you have areas within the same layer that are anomalous, and that's important, and I'll explain why as we go through to the cross section. So we'll take a look at the David prospect first. We're looking at a geological cross section. This is a geological interpretation that's been made by Chris at Big Rock Exploration, our field geologist, and this is comprised of knowing where the faults are and their orientation. So faults being basically a large crack in the rock, which is moving the rock layers in there's a lot of different directions that it can go. And then also measuring the dip and dip direction of these different beds as well. So measuring, okay, we've got the Seco sandstone, it runs for this long, and it seems to be dipping into the ground at this angle relative to the other units, and it's also dipping in at this sort of degrees, right? So using those measurements, then you can start to plot up what you think it's going to look like in the ground, and then interpret where your faults might cross-cut it and what you could be looking at there. So this is really the, I guess, the bread and butter of the presentation and the real importance of what we're saying here as well. And like I said before, the real foundation of the exploration project overall. Because we've got the Seco sandstone here. Now, for people that don't know much about uranium and uranium deposits, they can occur in a lot of different forms, but one of the most common styles of mineralization in uranium mineralization is sandstone-hosted uranium. So sandstone is always a favorable unit, lithological unit, because it's really quite porous. It's generally made up of quartz fragments, and you can stack a lot of quartz fragments together and then compress them so that they become a sandstone, but you still end up with a lot of space, relative, a lot being relative, a lot of space between those individual quartz fragments. And this allows for fluids to freely move through the layer. So sandstones are often aquifers and fluid conduits. And so when we have an environment like this, you can imagine something that's like let's say a slate, because a slate is relatively comparable to some of these other lithologies we're looking at, where it's made up of a super fine silt, which is then compressed and just packed down. And it's like a mud that's just been compressed into a rock. There's no room, and unless there's faults or cracks, there's no room for fluids to move through something like a siltstone or anything like that. But where there's sandstone adjacent to a siltstone, then the fluids can move through the sandstone there. So sandstones, sandstone-hosted uranium is something that a lot of us are familiar with, and that's what we're looking at here as well. Now with uranium mineralization, sandstone-hosted uranium, it can be sort of a tabular style deposit, or the sort of style that you're probably most used to hearing about is roll front. Now it doesn't really matter as much which style you're looking at, because they both very much need the same sort of thing, and that is for I guess oxidized uranium bearing fluids to come into contact with a reducing environment, and that's where it enables the uranium to actually drop out and precipitate. Otherwise it stays mobile in those fluids. So when you look at a sandstone layer like this that we see here, the Seco sandstone, and we've got a 10-meter wide zone here of that with a radiometric anomaly, this is really quite good, because this is telling us that we've had something like an oxidized environment where we've got some mobile uranium, and that it's come into contact with some sort of reducing environment, which has enabled it to precipitate out. All right, so this is a really encouraging sign. It means we've got the right sort of chemistry occurring here to potentially have uranium mineralization here in the ground. Now, when you look at the geological cross-section as well, there's a host of different areas and ways that the uranium mineralization could potentially occur. So we've got this top layer, KMVM. This is logged here as a minor coal unit. That's its, I guess, actual classification. To be honest with you, the geological team really calls this a trash rock, because this is something between a siltstone, mudstone. It's not really, doesn't know quite what it wants to be at this point. It has quite a high carbon content, and this is a reducing type of rock. Okay, so minor coal unit might not be the best actual description for it. The field team calls it a trash rock because it's not quite anything, but it is carbonaceous, and carbonaceous is reducing, and that's sort of one of the main things that we're interested in here. So we've got our Sego sandstone, which is dipping down to the ground. We know there's an area here where we've had some radioactive minerals form and drop out in it. And then when we look at the larger scale faults, which cross-cut the area as well, and I guess the direction that the ground has moved with those faults, we get an interpretation like this. Now, this is important because uranium can occur in a roll front style, like we spoke about before, a tabular style, but you can also find significant deposits here where along faulting, where the fluids have been able to move through the Sego sandstone. They move up and down throughout the fault, and where you have something like the Sego sandstone and the radioactive layer, which is in contact with this, directly in contact with this reducing environment, there's the potential there for them to be concentrated there in a sort of fault-bound structure or fault-bound deposit or something similar to that. So when you look at this as a whole, as an exploration geologist, you really think, aha, this is great, right? Because we have all the basics that we need to let us know that there's been uranium mobilization here. We've got uranium precipitation here in some form as well. And then we've got these geological structures in place, which give us multiple different styles of uranium mineralization for us to target and to chase. So this is, I guess, the real story of the announcement as well. And like I said, the bread and butter and the basis of the whole project is that we have this that we can pursue. So, there's multiple different targets here that you would go for. You can go for the actual Sego sandstone itself. You can try and target these fault structures, and also these contacts you see here, this carbonaceous shale units logged up at the surface here. So bound between those or in contact with those as well is another area for prospective uranium mineralization. So, this sort of interpretation to me as an exploration geologist just seems great. We've got some real banger of some targets to keep exploring. So the Moffat prospect, again, we see basically the same sort of setup. So large zone of Sego sandstone within a 10 meter wide anomalous zone, radiation CPS of 6,370. We've got interpreted faults which cross-cut it, which give us multiple different trap sites and a continuation. So, anywhere along this carbonaceous shale, we can have uranium dropping out here in contact with the minor coal unit we can have as well. In these faults, we can have fault-bound uranium mineralization or generally just roll front mineralization as well, further down in the Sego sandstone as we go. So, lots of prospectivity here, and it really starts to shape up to look really quite well. At Blue Mountain, there's two strong anomalies, one called Sego. I told you we're going to hear Sego a lot during this presentation. And then the Jacobson's targets, both of which receive CPS readings of greater than 2,000. Now, Sego actually had the strongest radiometric anomaly that we found through doing all this exploration, but it was actually undercover. It was under about 25 centimeters of soil, which doesn't sound like a lot, right? You think about a ruler, 30 centimeter ruler, it's about yay big. But what is interesting is that, and this is relatively well known, that you only need about 30 centimeters of cover to mask radiometric anomalies. And so the handheld detectors or just about all detectors really won't pick up that radiometric expression while it's got soil and things like that over the top of it. So what happened here is that Chris got, a small, very small anomaly and thought, oh, this is odd. There's no outcropping sandstone here. Started to dig down a bit, and then once he got, under 25 centimeters of soil, which is not much, found the sandstone and had a CPS of 10,000 odd, which is, the highest that we detected here and really quite good. So this is encouraging again because We know that I wouldn't say there's a lot of soil cover here, but there's certainly significant portions of this ground which have got soil. The Sego sandstone is not outcropping all the way. And so this just indicates as well that it's very likely that there are radiometric anomalies here which we can't detect just using simple surface sort of exploration means. And we really need to try and find a way to look beneath that soil and find more prospective layers and targets as well. So really good result just to prove that. Second target called Jacobson, returned a maximum count of 4,600, 500 CPS, which is lovely. So this is Jacobson here, and then we've got Sego up in the top northeast right hand side. Now you'll notice Sego is actually just a teeny bit actually off our tenements, and that's okay because all of the lithologies and all the beddings dip this way to the south and so run under and through our tenements as well. So the fact that this little surface, or not little surface anomaly, this quite strong surface anomaly is just a tiny bit off our tenement isn't really of concern because we know that all of the stratigraphic layers that are associated with that dip down into our ground. So still a legitimate target for us. But because he's only able to, I guess, find the Sego sandstone and measure it in that tiny little area that he's actually dug down, he can't map the extent and length of it. And so he can't try to draw up cross sections or anything like that. It's just very much here's these individual points, whereas Jacobson you can see it outcropping, so you can get a measurement of that width and then and do up the cross section. So that's why there's no cross section for Sego. So we'll take a look at Jacobson, and once again this is what I was talking about before as well. Multiple different Sego sandstone layers, but as I mentioned before as well, they're not all radioactive, which is excellent. So the fact that you've got one with no anomalous, no radiometric anomaly, but then you've got another layer adjacent to it, which is really excellent, because this is saying that this has had uranium bearing fluids move through it and this one hasn't, and that's what you want to see, right? We know where to target and we know the prospective layers as well, and it's just a sign that there has been uranium bearing fluids move through, like 100% there has been. So that's excellent. All right, and so lastly, we'll cover off on the Skyline prospect, which is probably my favorite name of all the prospects. No particular reason, I just think Skyline has a good ring to it. It's pure nameology. But the area consists of two significant anomalies, that being greater than 2,000 CPS, and one weak anomaly hosted in the middle to upper Sego sandstone. The Jackrabbit zone is exposed along a dipping slope, defined by contact with an altered and oxidized cross-bedded sandstone. So oxidized sandstone, exactly what we want to see, and if we can see oxidized and reduced sandstones as well in a bed, then that's even better. The slippery slope zone is a concealed radiation anomaly position in the middle of the Sego sandstone member. All right, Jackrabbit is a large radiation anomaly in bleached oxidized sandstone between two carbonaceous shale beds. The strongest radioactivity is near the contacts with the shales, suggesting a redox front, maybe down dip of the current surface exposure. Bedding is orientated, it gives you the direction there, and is expected to shallow with depth to the south. So this is the Jackrabbit here. The strongest readings are right at the contact here with these two carbonaceous shale units, which is pretty much to be expected as well. But what it does potentially indicate is that if you've got I'll just draw on this map really quite quickly here. So if you've got a radiometric anomaly peak here and here, or here and here, and not so much here in the middle, then this is quite good to potentially indicate roll front uranium. So a lot of you might be familiar with what roll front uranium looks like, but basically the uranium travels down through your sandstone. Where it's got contact here with these other units, you're going to get some precipitation, but then once it hits a reduced layer here within the actual sandstone stuff, it drops out as well, and you get much thicker mineralization down here. So if you've got something which is indicating you've got two limbs, which would be what potentially these two contact points may represent. I'm not saying they definitely do at this point, but it's just one of those early indications that it is what you're looking for. Then that can be a good strong sign of the potential roll front uranium mineralization there as well. So the roll front normally follows your sort of hydrological gradient here. And so you can normally expect your roll front to be sort of down, your roll fronts to be down and further down the hydrological gradient. So having these two limbs at the surface here is a good sign to start with as well. So again, two just more encouraging signs of the prospectivity of this area. The railroad target, one significant anomaly, upper contact of the Sego sandstone persists for approximately 200 meters at surface. So quite a large anomaly here, you can see here. But we don't have a cross-section for this one, unfortunately. So now I do want to talk a little bit about these counts. So the surface area is really quite good. I mean, that's the surface area of outcropping Sego sandstone, what he's been able to map on the ground. But I do want to talk a little bit about these count rates, the average count rates, and et cetera, just to, I guess, manage the expectation. Also, how I look at it as well as an exploration geologist, and pretty much how we all look at it. Now, I don't want people, I guess, to look at these CPS at these different prospects and necessarily think, oh, because this one is 6,000 and the other target was 4,000 or 3,000, that means that this target is going to be way better, as a better target than the others. You know, when you're taking these measurements at surface, these are exposed sandstone and exposed rocks, and they've had a lot of different weathering. They've been leached, bleached. There's been a lot of alteration which has happened at surface, which doesn't happen down dip and doesn't happen down there. So variation in the counts per second at the very surface, while it is a good indicator, I guess, of the strength of radioactivity, how much of an anomaly you're getting, it doesn't necessarily indicate how prospective that layer really is. What you just really want to know at this point is that, are these radiometrically anomalous, and do we have radiometrically anomalous zones within the sandstone itself, which would indicate that you've got that changing conditions that you need for uranium mineralization. And if the answer is yes, then it's really quite good. So, you know, I don't want people to read too much into 4,600 CPS versus 6,300 and start thinking, oh, that one's no good because it's only 2,000, this one's at 6,000. That's where we need to go, because it's just not, you can't just hang your hat on it that strongly. Yeah, because these surface indications, like I said, are really just indicating that the layer is anomalous and prospective, not like an accurate direct measurement of uranium abundance or potential or anything like that. So it's just important to keep in mind. I just don't want people, you know, going in with their blinkers on and thinking, you know, oh, this one's amazing and this one's no good. Obviously, the bigger and the higher CPS, the better. But when we're looking at it, the context, and we're keeping in mind what we're actually measuring here, it's really just the surface outcropping and not that strong an indicator of what could be down there, other than the fact that we certainly expect it to be radiometric anomalous down the sandstone layer as well. So I hope that makes sense. Now, with the rock chips as well, we've taken a host of different rock chip samples from here, but this is really a geological exploration project where we need to understand lots of different things about the project area, not just the radiometrics. And, you know, this isn't an exploration program where we've gone out and said, right, just go try and find the absolute highest counts per second and only take a sample of those to try and get us the best rock chip results. That doesn't actually really help us with our exploration and understanding what we're looking at moving forward. So a lot of the rock chips are taken of various different lithologies, reduced lithologies, oxidized lithologies, lithologies where we have a radiometric anomaly, other lithologies where it's not so strong, really trying to understand what these different rock types are that we're in contact with are, because that helps us understand the chemistry. And then as well, it will really help us try to identify a model, I guess, a mineralization model that we could be potentially looking at here. So, in this sort of area, you have Wyoming style uranium mineralization, and then you have a Colorado style mineralization as well. They're both a different age, and one's sort of tabular, one's generally roll front. I mean, they're using quite generic sort of terms there, but they have different pathfinders in them as well. So the Colorado style, is going to have vanadium as a strong indicator that it is that style of mineralization, whereas that's generally absent from pure sort of roll front or uranium style mineralization. So the purpose of doing these rock chips is really to, yes, get an understanding of what the rocks are and is there any mineralization associated with these radiometric anomalies. But really what we really want to understand is what sort of system are we potentially in, because one is, they have different shapes, the style of mineralization, and that really informs us sort of moving forward. So now moving forward with Skull Creek, obviously we've got those ALS rock chips to come in. That will be informative as well and help guide us. But there are just some other things here I wanted to point out. When I spoke about the SEGO target, which is under about 25 centimeters of soil, and the radiometric anomaly at surface was not very strong at all, go down 25 centimeters, and it's the strongest radiometric anomaly that we detected during this lot of groundwork. If you look at this portion of the tenement holding here over in the west, this is all pretty much under soils. All right, so with just the very first pass sort of ground exploration that we've done, we really have no way to detect if the Sego sandstone, which we pretty much know is interpreted to run through here, and pretty much know it does run through here, whether or not there are other targets in here which are just masked by the soils. So before we go ahead and mobilize drill rigs and spend all this money for, we really want to make sure that we understand where these targets really are, and then so that we're able to target the strongest and the most of them when we do go and mobilize the rig as well. So we've got some work to do to try and look undercover here to see if we can find any more anomalous zones under here. And then really there's no geophysical exploration data available for this whole area. So we need to obviously do radiometrics, see if we do an airborne radiometric survey, whether or not we detect anything here, because often with an airborne radiometric survey, you might actually pick up really quite subdued anomaly that's undercover, and then that will just help you say, okay, we need to go look here, here, and here, and then you can find, dig them up a little bit and find the stronger anomaly. So radiometrics is required as well. And to map these sorts of horizons, something like seismic is really quite useful to map these horizons, because the seismic waves travel at different speeds as they hit these different layers, and it really gives you a much better understanding of, all right, which layer do we actually have where are these faults really in like an interpretation, I guess, of the ground, and then where can our drill targets be, where do we want to try and hit that's most likely for us to get I guess any sort of fault bound mineralization as well. So these are the things that we're looking at doing now and looking at implementing. The team from Minor Geophysics sort of assessing this to work out the best path forward along with Big Rock Exploration, and then Mark Cousins supervising all of this as well to make sure that we're doing the right thing. And that's pretty much it, folks. I hope you found this informative or helpful, just to explain, I guess, the project overall and where we're at the moment. My contact details are at the end of the announcement here. It's my phone number, email. If you are a shareholder, if you're a prospective shareholder, you want to talk about the project or you want to know more, by all means, give me a call or send me a text. If you're media, want to organize interviews or get in touch or anything like that, touch base with Kelly Jo. She's amazing, and she'll be able to help organize and facilitate all of that as well. Again, too, if you do want to, you're always welcome to give me a call to discuss it. But if you want sort of a more detailed block of time for me to run through things with you, certainly get in touch with Kelly Jo as well, and she can help facilitate that. So Once again, thanks very much for listening to me waffle on. I hope you found the presentation to be helpful in some way. If you have any questions, just get in contact with me and we'll go from there. So, as I said at the start of the video, I do plan on doing these whenever we release a sort of a technical announcement to do with the projects and the exploration. So you can expect to see more of these moving forward. And that's it. So thanks for watching, and hopefully I'll speak to some of you soon.